I've talked quite a bit about how current is defined. Let me now talk about voltage. Okay. Let me clear this part up. Now, I've previously talked about how when we connect two parallel plates, to, say, a battery. Suppose I have a battery here as well. Okay, and this is connected to two parallel plates. So what the battery will do is that it will put positive charges on this plate that's connected to the positive pole and negative charges on the other plate. So in that earlier video about parallel plates, I've talked about how if you have a charged particle in between, for example, a positive charge, it will experience a force in between the plate. It will be repelled by the positive charges, attracted by negative charges. Right, there would be a uniform electric field in between, so this charged particle would accelerate. And let's say if it's a charge of 1 coulomb, for example, then and the voltage of the battery is 1.5 volts. Okay, then when it accelerates from one plate to the other, right, the electric force will do work on this charge and cause it to accelerate. And we think of the 1.5 volts as an electric potential. Okay, and the 1.5 volts tells us the difference in potential between the two plates. And if you recall what potential means the work done per unit charge to bring a charge from, say, a reference level to a certain point. So we had all these ideas previously. Okay, and this means that if this 1 coulomb of charge accelerates, is allowed to accelerate through this space from one plate to the other, the work done would be, okay, let's write this out. So this would be V. I would represent the 1.5 by V. I would represent the charge there by Q. Okay, and the work done from there to there, you remember, would be the charge times the potential, the change in potential, right? So the 1.5 volts would be the change in potential. Or we can also call it a potential difference. So this goes by various names. We can call this V here a potential difference, and it is also often called a voltage. Right? In either case, it's related to the work done, and in fact, it's the work done per unit charge to bring a charge from one point to the other. Alright, that has this potential difference. So if I rewrite this, I can rewrite this as V potential difference is the work done divided by the charge. So all this is familiar from previous videos about the meanings of electric potential and the parallel plates. So let's now take this idea and apply it to a battery connected to a circuit. Now this is perhaps a more familiar arrangement in everyday life. Many of us would have played with battery light bulbs and wires, or we might have seen them, and we don't often see a battery connected to two parallel plates with a charged object in between. So this is actually more common. Now let me think about this circuit. In this circuit, the battery would push a current through the light bulb, and the light bulb will light up. Now what I like to do is to think about the relation between this circuit and these parallel plates. See, the battery would also be 1.5 volts. Okay, so if charges is going, if it's pushing electric charges through the light bulb, it must somehow be doing work. Okay, now if I think about maybe between this point here and that point here of the circuit, so being connected to the battery directly, the potential difference between those 2 points would be 1.5 volts. And it means that in the same way as we did for the charge in between two parallel plates, if 1 coulomb of charge passes of maybe electrons pass through the light bulb, I can also think about the amount of work done in the same way as this, that the work done must be the charge times the voltage. Okay, because the voltage is related to the work and the charge by work done over charge. So that's my charge of 1 coulomb, and that's my voltage, V. So in this way, we have a relation for the circuit as well between the voltage of the battery and the charge that flows through the light bulb. Now that there is a difference from the parallel plate case. In the case of the parallel plate, the work done is it goes to accelerating the charge. So this work done becomes kinetic energy of the charged object. But in this case, there's the current flows steadily and it doesn't go faster and faster because there is resistance in the light bulb, and so the resistance is like friction to the electrons flowing. So the work done is the work done to overcome this resistance. Okay, and as a result, it's like overcoming friction. As a result, it generates heat and light. So in this case, the work done, okay, gives us heat and light instead of kinetic energy in this case. Okay, so there is this difference, but the way of thinking about potential and the way of calculating the work done is the same. Okay, so for example, if I have, in this case, if 1 coulomb if 1 coulomb of charge flows through the light bulb, and we know that the potential difference is 1.5 volts, it means that the work done is 1 coulomb times 1.5 volts, 1 times 1.5, so that must be 1.5 joules. And as we know, this is converted to heat and light, so the amount of heat and light produced, the amount of heat and light energy produced by the light bulb when 1 coulomb of charge goes through it must be 1.5 joules. In contrast, if I have a charged object of 1 coulomb between parallel plates accelerating from one plate to the other, no light and heat would be produced. Instead, the work done would go to increasing the kinetic energy, which in this example is also 1 times 1.5 joules. Right? So kinetic energy is 1.5 joules here, whereas here the heat plus light energy is the 1.5 joules.